So in this lecture, so let's talk about how to draw the resonance structures, so the actual resonance structures themselves. So I'll choose the example that we did in the last lecture. So I'll be choosing this example. So let me choose this example here. So in this structure we have many arrows, but we want to make sure that we choose one by one. So start with the first arrow. So when you move the first arrow, what happens to the structure? So notice that there were two electrons that are going to come here, so which means that it's going to be a double bond here. And nitrogen, because it loses the two electrons, notice the number of valence electrons on nitrogen. So it has 1, 2 and 3 and 4. So which means the nitrogen originally has 5, but it has 4 now, so it gets a positive charge. So remember that if it loses a lone pair, it becomes positive. If it gains a lone pair, it becomes negative. Now positive charge itself balances here, so we don't need to worry about this structure. Next, so we can write directly oxygen. So this is the first resonance structure. Next, let's do the second arrow. So the second arrow indicates from here to here. So where we have, so let me write down the structure. So when now, remember that in this structure, we are talking about this double bond going on to this structure. So there is a double bond going to be forming here, and the positive charge will get eliminated because it's just a double bond balancing for the structure. Now this carbon originally had valency of 4. Now it has a valency of 3, so it gets a positive charge here. So now that gets the positive charge. Next. So we have completed this and we have completed this. Let's look at the next arrow, which is for oxygen. Now so oxygen originally has, so it has one lone pair, so it goes here. Now oxygen now has a total of 6 electrons, so there is no charge on it. Notice that there is 1, 2, 3, 4, 5, 6. So there are 6 electrons on it, there is no charge. And the lone pair now becomes the 2 electrons on this carbon. So it becomes 2 electrons on this carbon with a negative charge. Remember that when you get a negative charge, you end up with 2 electrons. So now, so this part is also done. Sorry. So these two are done. Next, the last one is the final mechanism. So which shows the final mechanism. So let me. Right. So the last structure is for the last arrow, where the double bond donates its electrons to the nitrogen. So the double bond now originally has 2 pairs, nitrogen gets 2 lone pairs, so nitrogen gets a negative charge, and the structure that was originally there, so it had the carbon here, so the carbon here had 1, 2 and 3, so 3 bonds, and there was 1 hydrogen, but now there are only 2 bonds, which means that this becomes positively charged. So and you get so these structures. So these are the all possible resonance structures. So now there are chances that you might try and combine some structures, but you have to make sure that you remember that the idea here is to draw these structures first and then try to see which one is the better one. Now we drew all the possible resonance structures. So these are all the possible resonance structures that you can have for the given atom. Now what we want to know is which one is the most stable one. Notice that all of them cannot be stable, meaning that there is only one stable one. So how to find that stable one? So that brings us to the concept of assessing the resonance structures. So when multiple resonance structures can be drawn, so we know that we know a blend of all of them, the hybrid structure is the actual structure of the compound. So typically not all of them will contribute to the equally to the hybrid. So we use a list of rules in order of importance that allow us to determine the most significant resonance form for a given compound, so which we call the major resonance form. So what is the rule? So the first rule is the one with the most significant resonance form will have the greatest number of filled octets. Remember that octet represents that either it has 4 bonds or 8 electrons, right? So carbon here has 3 bonds, so it does not have an octet. Carbon here has 4 bonds, so that has an octet. Hydrogen has 2 electrons, so it has an octet. Again, oxygen here has 8 electrons, so that becomes an octet. Carbon here again has 8, so that's an octet. So that's total of 4 octets. Right? You don't even need to count hydrogen here, so you can write that there are 3 octets in total. Next, let's look at this side here. So this carbon has 1, 2, 3, 4 bonds, so that has an octet. Carbon here has an octet. Oxygen has 8 electrons, so 1, 2, 3, 4, 5. So sorry, 1, 2, 3 and 4. So that's 8 electrons, again octet. Carbon again octet. So this has 3 octets, this has 4 octets. So whichever has the higher octets becomes the major contributor. So in this structure, all of the atoms have an octet, so it becomes the major contributor. So whenever you have a carbocation, so always remember that whichever becomes the major structure will always become the one that has the highest number of octets. So in this structure there is a carbocation that does not have full valency, so which means that it does not have a full octet, so which ends up saying that it's not a good resonance structure or a minor contributor to the final hybrid. Next, rule 2. So rule 2 states that the structure with fewer formal charges is more significant. This comes in, so for example, when let's say when two structures have full octet or same octet, so number of octet. For example, look at it here. Carbon here has full octet, nitrogen has full octet, nitrogen here also has full octet, and again nitrogen here has full octet, and carbon here has full octet, nitrogen again has full octet. Note how am I saying this? Notice this nitrogen has 4 bonds, 2 hydrogens and 2 double bonds, so 1 double bond, so that gives it 8. Carbon again has 8, nitrogen here has 1, 2, so carbon here has 1, 2, 3 and 4, so that gives it 8. So there are 3 octets. In this one there is an octet for this nitrogen here, but carbon does not have an octet, nitrogen has an octet, which means this is going to be the first minor contributor, right? So this is not going to be the one that's major, so this is minor. Now both have 3 octets, which means that both have all octets full. Now we have to know the next rule, which is how to tie break this two. So to break the tie between these two, we use the structure with fewer number of formal charges. In this structure there are 0 formal charges, in this structure there are 2 formal charges. So this one, whichever has the least number of formal charges, becomes the major contributor. So in this structure, because there are 3 of them, what we generally do is we write the one with which is the most stable as the largest contributor. The next one becomes the major contributor and the last one becomes the minor contributor. For example, if you give a rank, this gets rank 1, this gets rank 2 and this gets rank 3. So this is how you rank the structure based on their ability to resemble the final hybrid. Next, the next one is if the compound has an overall formal charge, so focus only on drawing the resonance forms that show the delocalization of the charge. For example, if you have an overall formal charge, so only focus on the one that delocalizes the delocalization of the charge. For example, if you look at it here, this is an allylic lone pair. So then only choose the one that delocalizes the negative charge. For example, in both of them, we are only delocalizing the negative charge. The last one has insignificant resonance because this does not delocalize the negative charge, rather it causes more and more charges to create it. So that means that it's going to be an insignificant resonance form. Next, rule 3. So a structure with a negative charge on the more electronegative atom will become more significant. Now let's say in these two structures, notice that they have full octet. Both of them have the same number of formal charges, and both of them have delocalized the negative charge. And so both of them, all of them are tie. So what do you do? Next rule, and remember that this is a order of importance, meaning that the first importance is octets, the second importance is formal charge, the third importance is the delocalized negative charge, and the fourth importance now is where is the negative charge, so or the placement of negative charge. So the placement of negative charge should always be on the element with high electronegativity. The opposite is also true, which means if you look at the placement of positive charge, so positive charge should be on the less electronegative element. So between these two, oxygen has a negative charge here, and here carbon has a negative charge. Between an oxygen and carbon, oxygen has a higher electronegativity than carbon. So whichever one, the oxygen, if oxygen has negative charge, that becomes the major contributor. In the same way, if you have a positive charge between oxygen and nitrogen here, oxygen has greater electronegativity than nitrogen, so nitrogen should have the positive charge. So this is the rule 3. After fulfilling, if it does not fulfill the first or the second rule, then we come to rule 3. This is the idea for stability of the contributors. So let's take the first structure and let me write down all the resonance forms that are possible. So notice that this nitrogen has a negative charge. So if nitrogen has a negative charge, it has 2 bonds and 2 lone pairs. So there are 2 lone pairs and 2 bonds. Now what are the resonance forms that it can have? So the first rule we know is that it is in the allylic position, which means that it is an allylic lone pair. So what is the first arrow goes to? So from here it goes to the double bond, from the double bond to the adjacent carbon, the lone pair. So lone pair to double bond, pi bond to lone pair. So that causes it to get so you get a lone pair here and a double bond here, NH. So that when the double bond goes, the nitrogen gets 2 electrons. Now nitrogen has how many bonds? So it has 1, 2 electrons, 3 electrons, 4, 5. So which means that it has a total of 5 valence electrons. So that's its general valency. So we don't need to write any charge on that. But carbon here originally did not have a charge. Now it gets a lone pair, so it becomes a carbanion. Next, the other 2 bonds will stay the same. Next, again the same thing happens here. This one is an allylic lone pair, which means that this is going to go here. So lone pair to double bond to lone pair again. Now, so there's going to be a bond here and a lone pair here, and that lone pair will become negatively charged. Again, it's an allylic lone pair. Again, you will get a charge. So this goes, so pi bond to lone pair. So sorry, lone pair to pi bond to lone pair again. So again, that will end up displaying the final one. So you get the bond here, and this bond, this becomes the bond here. This bond goes away. You end up with 2 electrons right here with a negative charge. So again, the final structure will become let me draw the final structure. Again, notice that this is an allylic structure, so which means that lone pair to pi bond to lone pair again. So which creates the final resonance structure, which becomes Now, so you get a single bond, a double bond on nitrogen, so again it becomes a negatively charged one. So the bond here, here and here. So these are the resonance forms that you can get. So these are the common resonance forms. But notice that the first structure and the last structure is exactly the same. The reason is because if you do conjugated pi ring, you get the same structure back. So which means that this is going to end up forming the same structure again. Now this brings us back to the full resonance form. So these are all the possible resonance forms for this structure. So now we have the possible resonance forms. Let's try and apply each rule one by one. Notice that in all of them the octet stays the same because there is only electron movement and there is no positive charge. Because there is no positive charge, we can say that there is no, so there is all of them have a filled octet. Next, the second rule is here. So the second rule here is the structure with fewer formal charges. So we want to know the structure that has the fewest number of formal charges. Now notice that all of them have one formal charge. So all of them have one formal charge, so that also goes out. Next, delocalized negative charge. In all of them we are only delocalizing the negative charge, that also is gone. And come to the last one. The last one is the placement of the negative charge should be on the highly electronegative element. So here in this compound the negative charge can be either on carbon or nitrogen. But we know that nitrogen's electronegativity of nitrogen is greater than that of electronegativity of carbon. So which means that the negative charge should be on nitrogen. So there is the negative charge should be on nitrogen. So there are two structures where the negative charge is on nitrogen. So this is number one. So this is the major contributor and this one is also a major contributor. So all others, so all of these 1, 2 and 3, so all of these are going to be the minor contributors. So these are going to be the minor contributors. So there are 2 major contributors and 3 minor contributors. So this is how you assess the stability of a resonance structure. So and you can determine which one is going to be the most stable one. So here this structure and this structure are the most stable ones. So this is the most stable structure or the most stable resonance form. This was also the most stable resonance form. So this is how we can determine the most stable resonance form of any given structure. Now so try the following problems. So pause the video right here and try all of these problems one by one. And first thing that you have to do is draw the resonance forms. And second, apply the rules of stability. Remember the order of importance. So the first rule is filled octets. So the second rule is fewer formal charges, and the third rule is the placement of negative or positive charge. Right? So if it's negative, it should be on the higher electronegative element. If it is positive, it should be on lower electronegative element. So now pause the video right here and try to solve the problem one by one. So next, let's talk about the resonance hybrid. So remember at the start of this lecture, we talked about resonance. At the start of resonance, we talked about resonant hybrid, where it represents the pi bond of an allylic carbocation being delocalized all over the 3 carbon atoms. So this is consistent with molecular orbital theory because there are p orbitals on all of them, and all p orbitals will match and forming it to form a combined bonding molecular orbital. So where there are no nodes and spread out across all the 3 atoms. So now next let's talk about delocalized lone pairs. So what is a localized lone pair and what is a delocalized lone pair? So localized electrons are generally not in resonance. Delocalized electrons are in resonance and generally more stable. So to be delocalized, a lone pair must be adjacent to an unhybridized p orbital. So for example, if you look at this compound, there is a localized electron, so the electron pair here, which is adjacent to a double bond. So a unhybridized p orbital basically represents to a pi bond. Now, if it's adjacent to a pi bond, it generally ends up having a delocalized, becomes a delocalized lone pair. But that is not always the case. For example, let's take a look at the other structures. For example, here, the nitrogen here has a problem because it itself has a double bond and it also has a lone pair. So a molecule that has a lone pair and a pi bond, so does not undergo resonance. So does not undergo resonance. So this is one of the problems why when you have a lone pair and a pi bond, so then that atom will not undergo resonance. For example, look at this nitrogen here. Nitrogen also has a pi bond as well as a electron pair, so which means that it will not undergo resonance. So because this is not going to be a valid resonance structure. So whenever the only exception of a localized lone pair is when the lone pair also has a pi bond, right? So let's take a look at an example. So notice that this is far away from any other lone pair. There is no pi bond nearby, so it's a localized lone pair. Here there is a nitrogen lone pair. It does not have adjacent, so it's adjacent to a double bond. Here also it's adjacent to a double bond, right? So which means it's a delocalized lone pair. But let's come back to the last one, which is this lone pair on the nitrogen. The nitrogen here has a lone pair, also has a double bond, so which means that it's going to be a localized lone pair. So when a compound has a pi bond and a lone pair, it will not participate in resonance. So that's the only exception for a structure that has an adjacent double bond but by itself also has a double bond. So this is where the extra part comes in. So this is an example of a lone pair. So now, so use the following examples. So first thing you want to do here is identify first where the lone pairs are and how many lone pairs are there, and determine whether the lone pairs are localized or delocalized. So try for all the following examples. So pause the video right here and try for these problems. So with that, we end chapter 2, molecular representations.